Hello, welcome to today's video on complex numbers, specifically roots of unity, and in fact, even more specifically, we're going to be looking at using the special properties that roots of unity have to solve problems. Now, the thing about roots of unity is it's not the biggest topic in further maths A level, and it doesn't necessarily come up every year, but there's certain properties that roots of unity have. They can sometimes slip in as part of a big, much wider question that can sometimes catch people out because they just forget these properties and don't know how to use them. So that's basically what we're looking at today, ways in which we can use the roots of unity properties to solve particular problems, hence the title of the video, I guess. So kicking us off, the first sort of question we're going to look at is a question that is probably the most likely to appear as a direct exam question, solving a particular polynomial. So you might get solving a polynomial like this, and you'll see straight away it's written in Z's, which of course should straight away be a clue that we're probably, not guaranteed, but if we're writing Z's in a polynomial, it might be because there's complex solutions, and that will be the case here. Another way they might give you an even bigger helping hand is they might start sometimes using the letter W, which will give you even the further clue that it might be a roots of unity question, might again being the key term there, because the letter W looks a lot like omega. Of course, W is that, and then lowercase omega, the Greek letter, looks kind of like a very curly W. So anyway, how was this problem solved? Well, the way it's going to be solved is using the roots of unity property that says if we do 1 plus omega squared plus omega cubed, so on and so forth, all the way until you get to the final root of unity for whatever situation it is you're looking at, has got to equal 0. And that is important because that comes, if we have this property being true, then it implies that omega to the power of n equals 1. And the reason for that property existing, I'm sure you can look at another video to see where that property comes from, but all we need to realize for this question is that this equation is implying partially that z to the 5 equals 1. The reason that's important, you'll notice the highest power in the polynomial is 1 less than the power here. So the highest power I had here was 4, and so therefore I know the power of my polynomial down here will be 5. The other crucial thing to point out is that the solutions to this polynomial here will not be all the solutions to this. Instead, it will be all the solutions to z to the 5 equals 1, except for the solution of z equals 1. And why that's the case can be fairly easy to see why. Trying to plug z equals 1 back into the original equation, it's quite clear that that is not going to work, quite clearly. So therefore, we're not going to include that solution, but all the other solutions to z to the 5 equals 1 will be solutions of the original polynomial. So beyond that, you're finding what the solutions are. You're finding what the roots of unity are, and you can either view it as a special roots of unity question, or in reality, it's just like finding any roots of complex numbers, full stop, nth roots of complex numbers. So what we do is we go, well, obviously, z equals 1 would normally be the first solution we find. We're going to discount it, but that would normally be the first solution to z to the 5 equals 1, because that would normally be just 1 to the power of 1/5. But 1 is as a complex number, e to the 0i, and it's got technically a modulus of 1. But then to find all the others, remember all the other roots of a complex number are complex numbers with the same modulus, but an argument that's different by 2 pi divided by the number of roots we're going to be dealing with. The number of roots we're dealing with is the same as the power, so therefore 2 pi over n is the gap between each argument. As we've got a power of 5, that means we're expecting an argument of 2 pi over 5 in between each root. So therefore, the following roots are, I'm going to obviously stop writing the 1, of course, I wrote the 1 just for the example, modulus of 1 times anything to 1, so we don't bother writing out the front, but the other solution is therefore z equals 2 pi over 5i, e to the 4 pi over 5i, e to the 6 pi over 5i, and then e to the 8 pi over 5i. The final solutions are therefore just these four. We're not going to have the 1. As I said, we reject that one because it wouldn't be included. But there you go. That's one example of how a roots of unity property can be used to help ourselves, because it's a very specific case, but this polynomial does just convert to a much easier equation to solve, and then we can find the solutions. Just have to remember that z equals 1 wouldn't carry over. Okay, let's look at another sort of style thing that can be asked, and this is something that wouldn't be a question by itself, but these are things that might appear as part of the wider question, and just being able to see these things and recognize the implications of them is useful. So the first one is, if omega is a cube root of unity, the key bit being the terms of words there, what is the degree of the polynomial it satisfies? Key things there is the fact what it says in words. Cube root, well, that's implied we're talking about power of 3. So therefore, if omega is a cube root of unity and it's a solution to a polynomial, that's implying the polynomial is z to the power of 3 equals 1. And then for this one over here, we now have omega equals e to the 2 pi over 7i specifically. What is the degree of the polynomial it satisfies in this case? Well, a reminder that omega, we always pick omega as the solution to the polynomial that's got the smallest positive argument. So therefore, what we're saying is obviously that 1 is always going to be one of the roots of unity. And then we're saying omega is the first one that you get to going around anti-clockwise around the Argand diagram. So over here. Now, the crucial thing is that means we've got a gap of 2, in this case, 2 pi over 7 as the argument. Sorry, it's written very smallly. We've got a gap or an argument of 2 pi over 7 in between our first root, which is z equals 1, and our first complex root, e to the 2 pi over 7i. Now, as we know, the gap between all the solutions to, well, z to the n equals 1, style equation, z to the n equals any complex number. As we know, the arguments that separate each of those solutions to those equations is always the same. We know that the gap between omega and the next root along will also be 2 pi over 7. So we know this angle here, again, not very accurate diagram, but we know that argument there is also going to be 2 pi over 7, and so on and so forth until you've gone all the way around the full 2 pi radians. So therefore, a reminder that as we know, 2 pi over n is the gap between each solution to these equations. Therefore, we can find what n is the power of the equation just by doing 2 pi divided by what we know the gap to be. So therefore, 2 pi divided by 2 pi over 7 would just get us 7, and therefore we know in this case, if omega equals e to the 2 pi over 7i, we're talking about the solutions to the equation z to the 7 equals 1. Okay, so that's a little property that some of you might have to use. And then the last sort of thing we can do is we can end up using, or basically the two main properties of roots of unity, which are one which we've already quoted, which is if we add all the roots of unity together for a particular polynomial, then we end up finding that they add up to make 0. And then the other roots of unity property, actually, which we did mention earlier as well, is that omega to the power of n is equal to 1. Because if z equals omega is a solution to the equation, z to the n equals 1, then logically it follows that omega to the power of n must also equal 1, because if it must satisfy the equation, it must work in the equation. So using these two properties, we can sometimes simplify some algebra if we know something. So for instance, in this question, again, you're unlikely to get a question like this by itself, but it might appear as part of a wider question to help you, solve something. It's easier if, the algebra is as simple as possible. So in this case, to start off with, we're given that omega equals e to the 2 pi over 5i. So once again, similar to what we did just recently, just above, we know that if omega equals e to the 2 pi over 5i, straight away we know for this question the power of the polynomial this is satisfying is 5, because 2 pi divided by 2 pi over 5 is 5. It means we can fit 5 roots going around the full 2 pi radians on an Argand diagram. So therefore, that means for this specific question, we're looking at the following two properties. We can use 1 plus omega squared plus omega cubed, just adjusting that, plus omega to the 4 equals 0, because I stopped just before 5, 1 before 5, and then I also know that omega to the power of 5 equals 1. So how is that going to be useful? It varies question to question. In question A, we have omega to the power of 8. Now, 8 is quite a high power. Sometimes you might have to leave it like that, but in this case, we don't, because we know that omega to the 5 equals 1. So we know that this, by index laws, could be rewritten as omega to the 5 times by omega cubed. And as we know omega to the 5 is 1, that's why I decided to split it up this way, by the way, we know it's therefore technically just 1 times by omega cubed, and therefore omega to the power of 8 can be written more simply as omega to the power of 3. Part B, are we now looking at omega to the power of minus 3? That could also be rewritten in a nicer way, just because we generally don't like minus powers if we can avoid them. There's nothing dreadfully wrong with them, but if we can avoid them, a nice small positive power would be better. So to do this one, well, we know omega to the power of 5 is 1, and we know timesing by 1 does nothing to a number. So therefore, we would be allowed to write this, because that would be technically have an equivalent value. But wait a minute, if we multiply those two things together with the powers, we end up with omega squared. So it turns out omega to the minus 3 is secretly omega squared, and that's probably nicer to deal with and look at. Last one, a bit more tricky. We might have to use lots of different things here. We're not going to be able to, we can't really spot any obvious place where we can use instantly any of these things. We don't have a load of different omegas being added together clearly, so we can't just instantly use this property straight away. And then we don't see omega to the 5 anywhere, so it's not clear where I can plug that in yet. So the first thing I'm going to do is I'm going to multiply out the brackets, just because that'll be a quick, easy binomial expansion to do that. I'm still going to keep it in brackets though, because I need to multiply by omega again later. And of course, sorry, that should be a 3 there. And we have the plus 1 still, and we have the divide by 2. Now I've done this, I'm looking at it and going, wait a minute, we've got a 1, we've got a omega, got an omega squared, and we've got an omega cubed. They're all being added together. Now I know some of them have multiples, but we're starting to get this pattern here, but without the omega to the 4. So a rearrangement of this property would give us the fact that 1 plus omega squared plus omega cubed is equal to minus omega to the power of 4. That would help, because it would mean we'd be able to get rid of loads of different things and write them as just one thing. So using that property, I can rewrite the top bit as, or the stuff inside the bracket specific, as 1 plus omega squared plus omega cubed, because I know that's something I would like to have. But then realizing, no, I had the 1 and I had the omega cubed, but I actually had 3 omega, so I need an extra 2 omega added on. And I had an extra 2 omega, I had 3 omega squared, so I should have an extra 2 omega squared in my new expression here. Because what this then allows me to do is, as I said, replace all of that stuff with just minus omega to the power 4. So I could therefore write this as minus omega to the power 4 plus 2 omega squared. Instead of the plus 1, instead of the divide by 2. Okay then, so now we've done that, moving down. We could multiply out the brackets on the top. So we have minus omega to the power 5. We have plus 2 omega squared. We have plus 2 omega cubed. And we have plus 1 all over 2. Now, the interesting part about this is that now that we've done this, we can now see we've got an omega to the power 5, which means we can use this property here. Omega to the power 5 equals 1. So therefore, we know that as we've got minus omega to the power 5, that means we've got a minus 1 plus 2 omega squared plus 2 omega cubed, very dodgy 3 there, plus 1 all over 2. Of course, the plus 1 and the minus 1 are cancelling each other out, and then even nicer, that means we're just left with this, which means now the divide by 2 divides nicely, and so we're just left with omega squared plus omega cubed. So therefore, in the end, omega plus omega, omega times by 1 plus omega all cubed plus 1 all over 2 did just simplify very nicely to omega squared plus omega cubed. So, I mean, that was a bit of an extreme one. I'm not saying you get anything quite like that maybe in the exam, but it's just a good practice of using these properties, getting comfortable with using them, familiar of spotting them, of situations where you could use them, because that can appear as part of a bigger, wider question. Okay, hopefully this video is useful for you, and I'll see you again in a future video.